Okay, in today's lecture, we're going to talk about how we make the plots that we were talking about at the end of Monday's lecture. Those plots were called Bode plots. So let's kind of recap the story a little bit. So we've talked about this concept of a filter, which is to say that I take some sort of a signal, typically a signal that is a sine wave or is composed of multiple sine waves. And what I do is I pass it through a circuit of some kind, which has a transfer function h of s. If I'm talking about a transfer function h of s, right, so transfer function h of s, which we get from our circuit analysis. If I'm talking about a sine wave, I say s equals j omega, and I plot h of j omega. So in this case, what I have is a sine wave with an amplitude of 1, the phase angle of 0, at a frequency of 10 radians per second. And I pass it through a circuit that has this transfer function. Okay. In this case, at the frequency of 10 radians per second, the magnitude is 1 over square root of 2, or approximately 0.707. Okay, if I calculated that. And the angle of this transfer function is negative 45 degrees. So if I look at the output, right, the output is scaled by the amplitude of the transfer function. So in other words, my output is the same as my input. So my input was cosine 10t. My output is cosine 10t, but shifted by this angle, which is minus 45 degrees, and scaled by this magnitude, which is 0.707. So if I look, the peaks of this guy are at 1, peaks of this guy is about 0.707. That's the scaling effect. I see that the peak of this guy happens at time t equal to 0. The peak of this guy happens a little bit later because he's shifted by negative 45 degrees. So the act of filtering is basically to say we take signals and potentially make them smaller or bigger and shift them left or right. And depending on how much shifting and scaling we get depends on the frequency that we're looking at. All right, so we characterize filters as kind of being in a couple of different varieties, and there's others, but the critical ones are shown here. So low-pass filters, band-pass filters, and high-pass filters. So a low-pass filter passes all frequencies, or passes signals with all frequencies that are lower than a particular frequency. So here I'm saying omega c is our cutoff frequency. And what we're saying is that for all frequencies lower than omega c, signals are passing. And for frequencies above omega c, signals are being significantly attenuated, hopefully to 0. A high-pass filter is the opposite of that. A high-pass filter passes sinusoids that have frequencies greater than omega c and tries to kill off anything with a frequency lower than omega c. Now, a band-pass filter is one that basically only passes stuff in a small band and stops the low stuff and stops the high stuff. Now, these are our general sort of classifications, and I called them brick wall filters because they essentially look like a true brick wall. So I pass things and then I don't pass anything. Now, what we said the other day is in general that's not possible. All right, we never really have these brick wall filters. Instead, what they do is they roll off gently. So in this particular case, what you're looking at is a true low-pass filter, where I see that its magnitude is 1 at low frequencies, meaning its output and its input look the same. But as the frequency gets higher and higher, it goes towards 0 but doesn't quite ever get there. All right. We still call it low pass, though, because what it's saying is it's attenuating these high frequency signals, all right, and it's passing the low frequency signals. And where we kind of ended last time was we sort of said there's different kinds of low pass filters. So for instance, here's two circuits that are both low pass, and low pass from the input voltage to the output voltage. So in this case, from V in this source to V out across this capacitor. In this case, V in this source to V out across the capacitor. Well, this circuit here on the right is a second order filter. This one is a first order filter. What we see is that the second order filter's magnitude drops off much faster. Both of them are low pass because we see that their magnitude basically drops as frequency increases. That's what makes them low pass. This one just does it a lot faster. All right. In other words, it looks closer maybe to this sort of brick wall concept that we liked in our ideal filter. Okay. So we'll play with that concept a little bit more as we go. Now, where we ended last time was we basically said, okay, well, for most real circuits, in this particular case, I made this plot for a circuit that looked like this. I had essentially a current here, all right? I called this current IL, and I called this current IG. And what we're looking at here is IG over IL is equal to my H of S, okay? So in this particular case, when I plotted this, I said that the magnitude response went up as high as 70,000 and went down as low as 0, and that's really hard to see all of that in one meaningful plot. So what we where we kind of ended up is we said, well, we don't typically draw the magnitude. What we actually do is we draw 20 log of the magnitude, and we typically do that also on a logarithmic scale. So if I look at this, I see that between here and here, I've gone up a factor of 10 in frequency. So this is 1,000 radians per second. This is 10,000. This is 100,000. This is 1,000,000. So basically on evenly spaced points on the x-axis, I'm going up a factor of 10 in frequency. So we'll talk more about that as we go through. All right, these plots, these logarithmic plots are called Bode plots. And I want to explore a little bit more about how these plots are made. Okay? All right, so quick aside, before we can go too far down this line, I want to talk a little bit about the general concept of a transfer function. Okay? So transfer function, in general I can draw like this. So I have a multiplier in front, okay? And a transfer function would come from, circuit analysis of some kind. I look at a circuit, I get the transfer function. Okay? So I have H of S equals K times this monstrosity over here. And what I'm saying is I can basically always factor this transfer function so that I've got basically single poles on the bottom and single zeros on top, and possibly I have a bunch of what I would say poles or zeros at the origin. So maybe I have some single S terms, and I say plus or minus n because maybe I have 2 poles at the origin or 2 zeros at the origin, okay? So we're going to explain those terms a little bit more here in a second, but essentially you should probably already get the idea that because this transfer function is a polynomial of S, right? We talked about that before, this fact that this transfer function is a rational function of S, meaning I can have a polynomial on top and a polynomial on the bottom. What that means is that I should be able to take the polynomials on the top and the bottom and factor them into these sort of nice factors like this, okay? So in this case, what we do is we call the roots of the denominator, all right, we call the roots of the denominator poles and the roots of the numerator zeros, okay? And then we can potentially have these multiple poles or zeros at the origin, which is represented by this plus or minus n, s to the plus or minus n term. Okay? So to define that a little bit, let's give ourselves an example. Okay? So here's an example. H of s equals 10 to the minus 4s over 10 to the minus 5s plus 1. Okay, so a couple of things for this. Poles are, as we said, the values of s that make the denominator 0 or make the magnitude of this thing go to infinity. Zeros are the values of s that make the numerator and thus h of s equal to 0. So if I look at this example here, I can see very clearly that if s is equal to 0, the numerator's got to be equal to 0. So that is a 0. Okay? In this case, I see that in the denominator, if I have 10 to the minus 5s plus 1 equal to 0, then s has to be equal to minus 1 over 10 to the minus 5 or minus 10 to the 5th. All right, so I have a pole at minus 10 to the 5th. And so the way we tend to designate that is with a pole zero diagram here. So our pole zero diagram shows us basically where all the poles and zeros are located. So in this case, I've placed an O for a 0 at the origin because I've got a 0 at the origin. I have a pole at negative 10 to the 5th. So I've placed an X where that pole is located. This guy basically, this pole zero diagram is commonly made, and very often if you take control systems, we talk about this idea quite a bit of a pole zero diagram. The pole zero diagram basically tells me almost everything that the transfer function does. The only difference between what this tells me, this pole zero diagram, and the transfer function is I have this k value, 10 to the minus 4, that's out in front of this thing. I can't capture that 10 to the minus 4 anywhere. So you look in your homework, for instance, will typically give you some information about what this multiplier needs to be, and you'll have to figure that out. You can't capture that from this picture. So the critical thing is the O's here represent the 0 locations, and the X's represent the pole locations. O's for zeros, X for poles. Okay? All right, so we'll remember that, and we'll make use of that as we go through class and as you go through your homework assignments. All right, so to motivate how to make these plots, let's go back to my favorite circuit, the simple RC low pass. All right, so the simple RC low pass, if I look at this, we've gone through this before. If I do a voltage divider relationship, I have an input voltage. I take the voltage across this capacitor. So V out over V in. So if we do V out over V in is H of S, right? That's our transfer function. That's what leads to this particular 1 over SRC plus 1. Or if I'm talking about sine waves, remember this is the jump I make when I'm talking specifically about sine waves. The transfer function is something I write that applies to any waveform that I want to put in, okay? So if I'm talking specifically about sine waves, so for sine waves, I say S equals J omega, like that, and I move on, and I start to make my plots. Okay? Our goal, of course, is to try to see what does the magnitude of this thing actually look like as a function of frequency. All right, so let's take an example. Let's say R was equal to 1 kilo ohm and C was equal to 1 microfarad. Again, those are values that are pretty natural if we're talking in terms of an electronic circuit, for instance. All right, so if I plug in those values, I see that my RC value is 0.001, okay? So I have 1 over 0.001 S plus 1, okay? So in looking at this, the first question I ask myself is, where are the poles and zeros? Well, in looking at this, there's no value of S that will make this transfer function equal to 0. In other words, there is no value of S that makes the numerator 0. There is clearly, however, a value of S that can make the denominator 0, right? And I can see that if I have 0.001 S plus 1 equal to 0, I see that S equal to negative 1 over 0.001, or negative 1,000, is my pole location, okay? So I've marked that. I put an X here at negative 1,000, okay? So I know where my pole is. So that will come in useful later. My goal now is to basically say, how do I make these plots of the magnitude on a log scale, okay? Now, we talked about the benefits of logs before, right? At the end here, I talked about, well, it's really hard to see this vertical scale if I'm just looking at the magnitude. So instead, what I do is I plot 20 log of the magnitude. And the important thing is to plot the log of the magnitude. As I said before, we typically do 20 log of the magnitude for sort of historic reasons. Okay, so the benefit of the logs is they basically allow us to see what's happening in a much better way, which, as we'll talk about later, is really useful from a design perspective. All right, but there are two reasons why logarithms help us to make magnitude plots. So in other words, plotting the magnitude, right? If I told you that for the particular thing that we're looking at here, for this example, right, for the RC circuit, I would have this. If I did the magnitude of that thing, for my example, I would basically have to plot that magnitude, that function, okay? And that is the magnitude of it. So in other words, I'm saying that for this particular transfer function, the magnitude of that transfer function would look like this, all right? Plotting the exact value of this thing is not the simplest thing in the world to do. All right, it's not hard for a computer to do, all right, but it is hard to do by hand. Now, there's logs help us to make the plot by hand in an easy way. And there's two reasons for that. Reason number one is that we can make very simple approximations about a single pole or zero. So in this case, we have a single pole term, and we can make some really simple approximations about it. Similarly, if we had a single zero term, we can make some really simple approximations about it. Okay? All right, the other reason, which we'll look at in the second video today, is that the log of a product is the sum of the logs. Now, you learned that in high school, all right, but we're going to make use of that here today. So specifically what I mean is if I take the log of a times b, that becomes the log of a plus the log of b. And I consider this to be kind of a corollary result of that, right? If I take the log of a over b, that's the same as log of a times b to the minus 1, which means this becomes the log of a minus the log of b. Okay? So the fact that the log of a product is the sum of the logs becomes really useful later, as we'll see. Okay? All right. So let's look at an example here. All right, so we'll continue with this guy. So h of s is 1 over 0.00 s plus 1. Since we're only considering sinusoids, we let s equal to j omega. And this guy becomes this. So we said h of j omega is a function of omega. And in general, what I'm going to do is I'm going to call, I'm going to say that tau p is 0.001. Okay? So I'm going to define that thing as a tau value or time constant value. Okay? All right. So what I do is and let's just keep in mind for ourselves, I'm looking at the magnitude of this thing. So the magnitude of h of j omega is the magnitude of the top, right, which in this case is 1, divided by the magnitude of the bottom. So in this case, because I have a complex number on the bottom, I have the real part squared, so 1, plus the imaginary part squared. So I'm going to keep it as omega tau p squared, okay, where tau p is this 0.001. Okay? All right, so what I'm now going to do is I'm going to take 20 times the log of both sides, okay? So if I take 20 log of both sides of this, so 20 log of h of j omega is just simply 20 log of h of j omega. If I take 20 log of this guy, so again, remembering that the log of, right, we said log of a over b is equal to log of a minus log of b, right? I have, when I apply that, when I take, okay. So if I take 20 log 10 of this side, and I take 20 log 10 of, oops, log 10 of this side, okay, hopefully you see what I'm doing there. All right, so if I take 20 log of that, well, this guy's going into a funky mode for me here. Okay, there we go. All right, so I take 20 log of both sides. 20 log of the magnitude of h of j omega is just 20 log of the magnitude of h of j omega. So this case, 20 log of 1 over this square root becomes 20 log of 1 minus 20 log of that square root. Now the log base 10 of 1 is equal to 0, so I can approximate that away to nothing, and this whole thing becomes minus 20 log 10 of that square root term. The question is, what, if any, approximations can I make about that? All right, it turns out that I can. All right, so I'm gonna look at this thing essentially in two different ways. So this negative 20 log 10 of the square root of 1 plus omega tau p squared. I'm basically going to say I want to look at this guy in two different cases. The first case I'm going to say is let's let omega be much, much less than 1 over tau p. Okay? So in the other case I'm going to say let's let omega be much, much greater than 1 over tau p. So this would be what I would call over here low frequencies. And this guy over here would be what I would call high frequencies. Okay, so let's look at the low frequencies first. So in the case of low frequencies, if omega is much, much less than tau p, what's going to happen is this term right here. If omega is much, much less than 1 over tau p, what's going to happen is, if I look at this, that means omega tau p, so if I just rearrange this, omega tau p is much, much less than 1. Okay? Over here, on the high frequency side, I have omega tau p much, much greater than 1. Okay? So what does that mean? So if omega tau p is much, much less than 1, I look at this expression here and I say, well, if omega tau p is much, much less than 1, and then I square that number, it's basically the case that this 20 log expression becomes approximately minus 20 log 10 of 1. In other words, 1, this term here, is much, much larger than this term. So I can say that this guy becomes negative 20 log 10 of 1, which is basically 0. Okay? So what this is saying is that 20 log of the magnitude is basically equal to 0 for low frequencies. Okay, I'll repeat that. 20 log of the magnitude is equal to 0 for low frequencies. That's going to be an important result here later. On the other side, on the high frequency side, we have omega tau p much, much greater than 1. Okay? That essentially means that this term over here, this omega tau p term, is much, much greater than the 1. So that means that if I approximate this guy, if I can say if I have 1 plus a big number, that's approximately equal to the big number. Okay? So I would say that I can approximate this as minus 20 log 10 of omega tau p quantity squared. The square of the the square root of the square becomes minus 20 log 10 of omega tau p, like that, which again, because I have a product, I can write that as minus 20 log 10 of omega minus 20 log 10 of tau p. Okay? So let's remember what it is that we're plotting here before we go too far. We are always plotting versus omega, so we're trying to see what happens as frequency changes. So remember, we're plotting things as a function of omega. So omega is a variable. Tau p for all of our problems is always going to be a number. Like, so for the example we've been doing, tau p is 0.001. So it's like I can look at this as, just for a second, I'm going to call this x. So log 10 of omega I'm going to call x. So it's like I have minus 20x plus a constant. Okay? So what I have right here is y equals 20 log 10 of the magnitude of h of j omega is equal to negative 20x plus b. So it's like I have this sort of line, y equals mx plus b. Okay? So what I want to do is I want to make this plot. So I've found two results, and I guess this is the key thing I want to summarize here real quick. What I'm finding is that for really low frequencies, 20 log of the magnitude is basically equal to 0. For high frequencies, it looks like 20 log of the magnitude is something that decreases, right? It's going down. So as omega goes up, all right, this thing is going to go down. Let's see how that means, by kind of plotting this. So 20 log. So again, I want to so looking at my result here, I said I want to look at 20 log of the magnitude, and I plot it versus the log of omega. Okay. So what I just said there is, this is my y-axis, This is my x-axis, okay? And I have, basically what I'm going to do is I'm going to try to plot y versus x here. But I want to make sure that I get the axes kind of labeled correctly. All right, so in particular, what I'm going to do is I'm going to focus on the x-axis here first. So I'm interested in a set of frequencies, omega. And so what I've done is I've listed decades of frequencies, so 0.1, 1, 10, 100, 1,000. Okay? If I take the log base 10 of each of those, you should be able to calculate and prove to yourself that the log base 10 of 0.1 is -1, the log base 10 of 1 is 0, log base 10 of 10 is 1, and so on and so forth. What I see is that each decade in frequency, so each factor of 10 in frequency, is basically going up by 1 on the log scale. So because I have shown this x-axis on the log scale, what I'm going to do is I'm going to on the top side, I'm going to write the log of the number. So the origin is 0 right there. Frequency-wise, that is 1 radian per second. Okay? So then I'm going to put the number 1 here, and then the number 2 here, and then the number 3 here, and the number 4 here. The number 1 on the log scale corresponds to the actual number 10. The number 2 corresponds to the actual number 100. The number 3 corresponds to the actual number 10 to the third. And 4 corresponds to the actual number 10 to the fourth. So notice that my origin on this log scale corresponds to 1 radian per second. Not 0, but 1 radian per second. All right? So if I were to go on the other side of the origin, right, this guy is -1. This would be 0.1 radians per second. -2 back here would be 10 to the -2. Notice, if I took the log base 10 of 0, that's undefined, right? That's actually approaching negative infinity. So 0 is all the way back there, right? Or I should say, on the top side, so the number 0 is all the way back at negative infinity on this scale, so it's really hard to see. Now, on my y-axis, I'm going to mark off 20. So here's 20, here's 40, and down here I'm going to say -20 and -40, okay, and maybe -60. Like that, okay? Now, what I want to do is I want to use my approximations for this original transfer function, okay? So the approximations I had, as I said, for low frequencies, 20 log of the magnitude, which is my y, all right? 20 log of the magnitude is equal to 0, okay? So the question is, what are low frequencies? Well, I said low frequencies are for anything much, much less than 1 over tau p. So 1 over tau p, in this case, is the same as our pole value, right? It's 1,000 radians per second. Okay? 1,000 radians per second. So, frequencies much, much lower than that, everything is equal to 0. So what's much, much lower than? I don't know. Let's say it's less, let's say it's up to 100, okay? So what I'm going to do is I'm going to try to draw in here, right at 0 up to 100, okay? That's what I think must be happening. Now for high frequencies, okay, what did we say? For high frequencies, it basically looks like I have y equals 20 times the log of omega plus some constant. And because I'm plotting versus log of omega, I can view log of omega as just a single number, x. So it's like I'm plotting something that is -20x, okay? So what would that look like? Well, for high frequencies, so high frequencies in this case, I'm going to say, well, that's at least a factor of 10 greater than the frequency I'm talking about. So in this case, right, we were talking about 1,000 radians per second. So let's say what this means is that for 10,000 and above, I must be falling, I must have a linear graph that is falling at a rate of -20. That's its slope, okay? And so what's that going to look like? I'm going to say it looks like this. I'm going to draw a little bit further here. So here's 10 to the 5th, 5, 10 to the 6th, 6, okay? So what I'm going to say is at these points, I'm falling. So if log of omega is my x-axis, then between 4 and 5, I fall off 20 dB, right? The units here are dB. That's the units of 20 log of a number are dB. So this slope right here is -20 dB in 1 decade of frequency, right? So as I go from 10 to the 4th to 10 to the 5th, that's 1 decade, and I fell -20 dB. And then as I go from 10 to the 5th to 10 to the 6th, I'll drop from 40 to 60. All right? So in other words, I'm drawing at high frequencies, I'm drawing a line that is dropping at 20 dB per decade. I'm drawing a line with a slope of -20. For low frequencies, I'm drawing a line with a slope of 0. It's a constant. Question is, what happens when frequencies are neither high nor low? Well, let's just make an approximation that low frequencies hold up until I get to 10 to the 3rd, and then the high frequencies hold up everywhere after. We'll make that approximation. Okay? And then if we want to know if our approximation is right, what do? Well, we go to the computer and we plot the actual values. In other words, we make no approximations. We don't do this low frequency, high frequency business. We just plug it into the computer and see what it tells us. Well, if we do that, here's what we get. Okay? So the blue here is the actual magnitude response in dB. The straight lines are what I've shown here with the black. And you can see this. Let's follow this. So we start at low frequency on the left. So in this case, we're starting at 10 radians per second. Okay? So at 10 radians per second, we're at 0 magnitude, 0 dB magnitude. As we get to here at 100, we're at 0 dB magnitude. By the time we get to 10 to the 3rd, I see that this guy has dropped a little bit. The blue, the actual, has dropped a little bit. But then he starts to curve down and to drop and to fall. If you look at my sort of approximation here, my straight line or asymptote approximation, what I see is I said that it was flat out to the exact location of this pole frequency, and then it starts to drop at -20 dB per decade. Okay? And let's validate this 20 dB per decade business. So if I look at this, here's 10 to the 4th. So at 10 to the 4th, I see that the magnitude is equal to -20. 10 to the 5th, a decade later, my magnitude is at -40. So I can say that the slope of this guy is -20 dB per decade. Okay? All right? So what I notice is that the actual graph and the approximation are pretty close to each other, except near these what we call breakpoints, where the slopes are changing. Okay, there's a key reason for that. Basically, our approximation is kind of breaking down. All right, but for design purposes, this sort of concept of the straight line or asymptote approximation is really, really useful. Okay. Now, what I want to do is go into the other reason why this log graph is useful, and I want to exploit this particular result. I'm going to stop our video here and allow you guys to take a break and myself to take a break, and then we're going to do part 2.